everybody, welcome back to another Gregorious Maths video. Today I'm doing a video that's been long overdue, okay? I've literally, tried to film this video 2 months ago. I was technically correct with everything, but, I don't know. I just didn't like the video, then I kind of forgot about it. And now that I'm doing number theory, and someone in Black Pen Red Pen's comment section was asking for a generalization of this. And then I thought, hey, I know how to do that, why not make a video? So here we go. We're going to be generalizing zeta of 2k. But to do this, we're going to look at two seemingly unrelated functions. And yeah, it's going to be great. So, now, remember that sine of z equals z times the infinite product from k equals 1. Sorry, let's go from n equals 1. From n equals 1 to infinity of 1 minus z squared over n squared pi squared. Okay? Now, taking in the natural log on both sides makes this a product a summation. So actually, we're going to begin by deriving what's called I think it's the Laurent expansion for cotangent of z. Okay, and the first step is to look at ln of sine of z. Not sin, sine of z, okay, equals ln of z plus the sum from n equals 1 to infinity of 1 minus z squared over n squared pi squared. Okay? Great. Now we differentiate term by term. Leaving us with an expansion for cotangent of z, but you'll see that we can do much better. Oh, sorry, of ln of this stuff. Sorry, for some reason I'm having trouble writing a minus sign. Alright, anyway, so this implies, we're just going to differentiate term by term, okay? That cotangent of z equals 1 over z plus the sum from n equals 1 to infinity of, differentiate the outside, that's 1 minus z squared over n squared pi squared to the negative 1 times the derivative of the inside is negative 2z over n squared pi squared. So we bring the minus out to the outside times 2z over n squared pi squared. Okay, now this is an expansion, right? But if we zoom in on the inside of this sum, we can do better. Okay? Now, let's look at this. We'll look at it in blue. Okay? 2z over n squared pi squared times 1 minus z squared over n squared pi squared to the negative 1. Well, this part here is just some number. This is actually 1 over 1 minus this. And that will ring a bell if you've learned infinite geometric series formula, which if you're watching this video you probably have. Okay? Because this is the common ratio. Okay? So actually this part can be written as an infinite summation. So this equals 2z over n squared pi squared, okay, times the sum from k equals 0 to infinity of z squared over n squared pi squared to the power of k. Now we can do better by distributing this in and shifting the index. So this equals, let's just distribute this in and then we'll shift the index. So this equals the sum from k equals 0 to infinity of Now, we'll leave the 2 out front. Okay, there's 2 here. Now, z to the 2k plus 1 over n to the 2k plus 2 pi to the 2k plus 2. And now when we shift the index, this equals 2 times the sum from k equals 1 to infinity of z to the 2k minus 1 over n to the 2k pi to the 2k. Why? Because we need to start from the same point, right? So when k equals 0, this exponent is 1. So we want it to, when we shift the index, we want the exponent to still be 1 when k equals 1. We solve the simple equation, we get this. And we use the same reasoning for the denominator. And now when we plug this into that, this whole thing implies that cotangent of z equals 1 over z minus 2 sum from k equals 1 to infinity of the sum from n equals 1 to infinity of this chunk here, z to the power of 2k minus 1 over n to the 2k pi to the 2k. Okay, and now remember that these two are just constant in the n world. We can bring them out here. What we're left with will be the sum from n equals 1 to infinity of 1 over n to the 2k. But that's just zeta of 2k. So this equals 1 over z minus 2 sum from k equals 1 to infinity of zeta of 2k times z to the 2k minus 1 over pi to the 2k. And now I'm going to write this at the top of the board, and we're going to look at a seemingly unrelated function, but will turn out to be the trick to evaluating zeta of 2k. So now that we've derived this, when I was writing it out, just beautiful expression, okay? I really love when we have a sum of a special function. I just really like that. I think it's really cool. Like when we derived the polygamma thingy and it had the sum of a zeta function. I just think that's really beautiful. Okay, now anyway, let's look at e to the t. That's equal to 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus so on, so on, so on, implies that t over e to the t minus 1 equals, well, let's do e to the t minus 1, okay? That gets rid of this one. Division by t subtracts 1 from all of these powers, and taking the reciprocal leaves us with 1 plus t over 2 factorial plus t squared over 3 factorial plus all to the power of negative 1. Okay? Now, this series here is equal to the sum from m equals 0 to infinity of b sub m over m factorial times t to the m, okay, where b sub m are the Bernoulli numbers. And I'm not going to go into evaluating them in this video, but they're just a special sequence of numbers. I'm sure there's a Wikipedia article about them. Okay, now, note that this, okay, we're just going to keep this in mind and this in mind. Now, we're going to manipulate this expression here. T over e to the t minus 1. Notice that this is t over 2 times e to the t plus 1 over e to the t minus 1. And then this minus 1. Okay, you can check for yourself that this works. Okay, now this equals t over 2 times hyperbolic cotangent of t over 2 minus 1. Okay, because the trick is we multiply top and bottom by e to the negative t over 2, and then it will just be precisely hyperbolic cotangent of that minus 1. Okay, and now using the complex definitions of sine and cosine, okay, this equals t over 2 times I cotangent of it over 2, and then minus 1. Okay, this just comes from the complex definition of cotangent. Now, putting z to be it over 2, to clean this a little bit up, this equals z cotangent of z plus iz. Okay? Because remember, we still have to distribute this t over 2 into here. Okay? And if z, let me just write down in a pink, for example, z equals it over 2. Now division by z and subtraction of I, in this equation here, implies that the cotangent of z is equal to negative I plus 1 over z times, is equal to negative I plus 1 over z sum from m equals 0 to infinity of the mth Bernoulli number over m factorial times t to the m, which equals negative I plus the sum from m equals 0 to infinity of b sub m over m factorial times. This here is 2z over I to the m. Now this 2 over I to the m can stay, and 1 over z times z to the m is z, so we keep our 2 over I to the m, and this is z to the m minus 1. Now, the grand finale. We can finally compare this and that. And this is where it gets exciting, because this is where, you should be tense with anticipation. What's the final result going to be? Comparing coefficients, setting m equal to 2k, which is greater than or equal to 2. Okay, I'm not sure why I wrote that. Setting m equal to 2k, we can compare coefficients. This part here is equal to this part here. So overall, and don't forget the negative 2. So negative 2 zeta of 2k over pi to the 2k equals this right here. B sub 2k over 2k factorial times 2 over I to the 2k. Now I want you to notice that because this is to the 2k, this is like 2 squared over I squared to the k. 2 squared is just 2 squared, and I squared is negative 1. Okay, so we're actually left with 2 to the power of negative 2 to the power of 2k. But I'm just going to leave it like this for now. Okay, so now we want to get zeta of 2k on its own, which is quite easy. This implies that zeta of 2k equals, this thing of course stays on the top, b sub 2k. Multiply this on both sides, pi to the 2k. Okay, it's all going to be over 2k factorial. Okay, now division by negative 2 subtracts 1 from the power, so we get 2 to the 2k minus 1. And of course, but division by negative 1 of this leaves us with negative 1 to the k minus 1. And this is our desired expression. We have a closed form for the generalized version of zeta of 2k. This was a crazy ride. We derived along the way this beautiful expression for cotangent of z. This pretty nice expression for cotangent of z. I never realized cotangent of z could be so crazy. But here we are. We have arrived at zeta of 2k in its generalized form. Now, I highly encourage you to read the Wikipedia article about the Bernoulli numbers, or anything you find helpful, so that you can find, the first 10, the first 10 even zeta numbers or whatever. I'm not sure what I'm saying anymore. Like, for example, zeta of 2 is pi squared over 6. Zeta of 4 is pi to the 4th over 90. Zeta of 6 is pi to the 6 over 956. Those are all the zetas I can remember. That even at positive integers. But yeah, do your research about the Bernoulli numbers. And yeah, this is our really crazy closed form generalized version of zeta 2k. Goodbye.